It's a great pleasure to be the first speaker of this conference. And it's always so nice to be back in Cambridge. So let me just see if I can get this one to work. Okay, so I'm going to talk about planet formation and particularly on models that connect the formation of planets to the outgassing of the primordial atmosphere of rocky exoplanets. And I can go one forward here. Now, of course, a great motivation to study planet formation is this ongoing detection and characterization of exoplanets. And of course, as we all know, the first exoplanet was discovered in 1995, and this was then given the Nobel Prize in Physics to Michel Mayor and Didier Queloz in 2019. And today, astronomers know more than 5,000 exoplanets. I'm just showing some of them here. This is from the Kepler survey that are showing the period of the planet here and then the radius of the planet. 1 being Earth, 4 being Neptune, and 10 here being Jupiter. And we just see this kind of big population of planets that are known now. But if you focus out on the region that is in the habitable zone out here where water could be liquid, you also see we're running a little bit out of planets because they're basically harder to find. So we can change this plot a little bit and we can go and look at the insolation instead. So the insolation is the amount of radiation we see from the star relative to what the Earth receives. Earth is 1. Venus is approximately 1.5, and Mars would be something a little bit less than 0.5. And then you see we have far fewer objects here. This is, by the way, only low mass planets here. We have a few handful of objects only that are in this so-called habitable zone where liquid water could be liquid at the surface. One of them, Proxima Centauri b, which is orbiting around a nearby very low luminosity star. So this is sort of a challenge now, I would say, in planet formation to explain, to go a little bit beyond this and go over to this and say, how do these planets form, and particularly what can planet formation predict about the composition of the atmospheres, because we want to understand eventually is there life around any of these, and then we also want to understand what does the atmosphere look like in terms of habitability. Okay, so planet formation is a process that works by dust grains colliding together and to form larger and larger bodies, eventually accreting gas also. It takes us over 13 orders of magnitude in size, from sort of micrometer-sized dust all the way up to planets of 10 to 4 kilometers in size. This happens around young stars in protoplanetary disk. And the first step is that micrometer and nanometer-sized dust particles collide and stick together to form pebbles. And then I'm very motivated by 3 questions in planet formation theory, is how pebbles come together to form planetesimals, like Lutetia here, which is an asteroid, which I will not talk much about today. I actually did a lot of work on that in my career. But I want to focus on the next 2 steps, is how do planetesimals grow to form planets, so it's like a twin Earth here, and what are the conditions on the surface of these potentially habitable planets? What does theory predict, maybe even before we start to observe these? So, as I said, planet formation takes place around young stars in protoplanetary disk. This is what you see with the ALMA telescope when you point at young stars right now out in the universe, surrounded by beautiful disks of gas and dust. It's called protoplanetary disk. What we're seeing here is the thermal emission from cold pebbles of millimeter sizes. They are approximately 100 AU in size. It's a 10 AU bar here, approximately the scale of our solar system. And importantly, we are not seeing the gas here at these temperatures, a few 10 to a few 100 Kelvin. Hydrogen and helium is completely invisible. What we're seeing here is the thermal emission from dust and pebbles that is basically re-emitting the radiation that they receive from the central star, now in the millimeter and centimeter wavelengths. Now, these pictures are all nice. We can do statistics on them. We can measure the total emission, convert that to a total mass, and poof, we can make a cumulative mass distribution here. And let me just explain here first. Class 0 and class 1 disks are young stars, less than 1 million years old, very, very young. And class 2 are stars that are almost losing their disk. They're a few million years old. Here's a cumulative plot from Tikhonik 2018. It's the log of the dust mass in Earth masses, 0, 1 Earth mass, 10 Earth masses, 100 Earth masses, 1,000 Earth masses. And you can see how young stars basically are surrounded by disks that are a few hundred, maybe up to 1,000 Earth masses of solids, mainly millimeter-sized pebbles. And then with time, this falls very quickly, over 3 to 4 million years maybe. This falls to a few Earth masses only. So something happens in those 3 to 5 million years. Mainly gas and dust is accreted onto the star. And that's why I say planet formation is a race against time. You need to form planets while these disks are still available. All the disk material is still available. So both planetesimal formations, so from dust to planetesimals, and also from planetesimals to planets, must happen in these few million years. Now, traditionally, people have made planet formation models by saying, look, that was dust, it turned into planetesimals, and now these planetesimals will collide together to form planets. And I just want to show on the next slide why this has been shown to be problematic, and then I'm going to come out with an alternative model. So what is the problem with making planets only by accreting planetesimals? The problem is that it's very inefficient. I'm showing here actually a classical paper by Tanaka and Ida from 1999. It's a very nice paper with some very impossible to understand non-dimensionalized units. It doesn't matter too much here. It's just the distance from the star here relative to a starting position. And you see in an n-body simulation, the protoplanet is migrating towards the star. That's because of the gravity from the protoplanetary disk. It's migrating towards the star, and ideally it should accrete a lot of these small planetesimals around, but what happens is that it scatters them in front, it scatters the planetesimals behind, and as it moves through, it sort of makes a gap in the planetesimal population. It doesn't really accrete planetesimals very efficiently. Now, Tanaka and Ida, they actually took these simulations and they gave sort of an efficiency of accretion out of these models. But together with Bertram Bitch, who is now at Cork, in 2019, we decided to take these models and check, can we form the solar system? The solar system is actually a very challenging system to form, so we should always start with planet formation to see, can we form the solar system? Then, if we can do that, then we can continue with the exoplanet. Okay, let's start with Jupiter, 5 AU, 300 Earth mass. It sits here. Now we can make a growth track. We start here at 5 AU and we run this kind of model, and if the planet is growing up to around 10 Earth masses, then it starts to accrete gas and grows to a few hundred Earth masses. It follows the blue line. The planet migrates so much that it forms something like Jupiter, but in a very close orbit, very close to the star. That's because of the gravity from the protoplanetary disk, basically. So it didn't really work well to form Jupiter. Now we can say that's fine, we need to migrate, therefore we should start to form further out, but then the inefficiency of this process really sets in. It's a real problem further out, and at 10 AU you hardly grow more than 0.1 Earth masses. At 15 and 20 it's completely impossible. So you see, Jupiter is a real challenge, Saturn is near impossible, and Uranus and Neptune you could basically forget about it with the classical model. Now, of course people have been aware of that, and when people run these models they will say, well, maybe you can go to smaller planetesimals, maybe down to 10 meters, 100 meters, that will certainly help. But then I would say this is inconsistent with the solar system, where planetesimals were born at 100 kilometers in size. So we need to rethink this. There's a real issue here. And I just want to say this is just a one-dimensional model, and actually it confirms n-body results by Tanaka, Ida, Thomas, and Levison, and by other groups. So this issue is why our group and many other groups in the world around 10 years ago started thinking about pebbles again. Can pebble accretion be more efficient than planetesimal accretion? And it can. So originally we thought that planets grow only by collisions between planetesimals. But you see the issue here. Here's a growing protoplanet. Here's the Hill sphere. This is from our annual reviews paper in 2017. Here's the Hill sphere. Here's the planetesimal that the protoplanet is trying to accrete, but what happens typically in a two-body process is just a scattering. It's not very interesting. Most of the time you just scatter the object. Actually hitting the protoplanet is very unlikely. Replace the planetesimal by a pebble, and the pebble feels gas drag. That means as the pebble is moving past the protoplanet, it feels drag from the gas. It loses kinetic energy, and at some point it has lost so much kinetic energy that it gets gravitationally bound to the protoplanet, and then it has no choice but to spiral in and hit the protoplanet surface, as we see here in this illustration. Yeah, just a bit of a joking analogy here. It's a little bit like the biggest mammals on Earth living from eating some of the smallest creatures on Earth. So big planets growing by eating small pebbles. It's called pebble accretion. The idea is that planets that grow by accreting pebbles can actually outcompete the migration. And then we can try to make the game where we take the exoplanet populations here with super Earth and hot Jupiters and cold Jupiters and ice giants and even Earth-like planets. And we can see we can make it now with a simple model where we form one planet at a time. I should, by the way, emphasize here that the way giant planets grow is by accreting a core first, a solid core around 10, 20 Earth masses, and then it accretes gas afterwards. So there's both core accretion and gas accretion and also migration. Let's start here nominally with the dust to gas ratio 0.01, and we get this population. Now, you see, there's a little bit of a similarity. We do get the super Earth here, we get the hot Jupiters there, but we do have trouble here with Jupiter, Saturn, Uranus, Neptune. Solar system, always hard to form. We can then go to a little bit higher metallicity. At this point, there are more pebbles. Pebble accretion rates are higher. Migration rate is the same. Therefore, planets become more massive and end up further out. And now you see nicely Jupiter and Saturn being characteristic solutions of the pebble accretion problem here. Uranus and Neptune are still a little bit hard, but we also think that they probably migrated outwards later by accreting planetesimals, the so-called Nice model. So maybe it's okay that they are hard to form them at 20 and 30 AU, but maybe they form at 15, 20 AU. But what I wanted to bring you to go forward from this plot is the following. You hardly see them here, but actually Earth and Venus there and there, they are very easy to form by pebble accretion. So this actually opens another question. Did Earth form by pebble accretion? Even though collisions are very inefficient, so close to the star, Earth could certainly well have formed by collisions between planetesimals. There are hundreds of Earth masses of pebbles moving in through the inner solar system during the protoplanetary disk phase, so that it's actually a real possibility that Earth is forming via pebble accretion also. And why should we care? Earth could have formed by planetesimal accretion or by pebble accretion. That's fine. There are two ways to form Earth then, but there are actually some major implications of if terrestrial planets form via pebble accretion. With in traditional planetesimal accretion, it takes maybe 30 to 100 million years for Earth to form via mutual impacts between planetesimals and giant impacts. With pebble accretion, Earth forms much faster, actually within the protoplanetary disk, in just 3 to 5 million years. That's one thing. Maybe more importantly, pebble accretion gives a new way to deliver volatiles to Earth, and those volatiles are, of course, what make the atmosphere and what would be essential to life. Because with the classical model of terrestrial planet formation, Earth forms dry by accreting planetesimals, and then it accretes maybe a few random impacts of asteroids from the outer regions of the asteroid belt that are icy. And this gives us a broad distribution. This is from Raymond 2004, a broad distribution of water delivery to terrestrial planets between very dry, less than 1 Earth ocean, or maybe up to more than 100 Earth oceans. So it's stochastic distribution, and it's very unpredictable. And the amount of water that Earth has is then a random thing. With pebble accretion, on the other hand, pebbles are accreted with a rim of ices and organic molecules. And as these pebbles are raining down into the magma ocean, into the molten planet here, they are then delivering their volatiles into the magma ocean. And when the volatiles are delivered by gazillions and gazillions of pebbles instead of a few giant impacts, then it actually becomes much narrower distribution. So volatile delivery on pebble rims is a calculatable consequence of planet formation. So that's a huge difference. Got it? Okay, let me go a little bit more details about this volatile delivery mechanism via pebble snow. So this is just an illustration I found on Google of a dirty hailstone that fell on Earth. But you could sort of imagine that pebbles might look something like this. There's a solid inside, then there's a big ice rim, and the ice rim is maybe filled with some organic goo also, not life, but organic molecules that carry carbon and nitrogen. Yeah? And as these pebbles are then accreted down through from the protoplanetary disk down through the magma ocean, they're undergoing thermal processing. So the idea here is that the planet is sitting in here, it has a molten core, it has a molten magma ocean, then it has out to the hill radius, that's like 1,000 planet radii. From the planet radius out to the hill radius, there's 1,000 planet radii. The first 100 planet radii approximately is a convectively bound envelope. You see it here in actual hydro simulation. You see the circulating flow here. There's a bound envelope of gas here. And out here in the 90% outer part of the hill radius is what we call the recycling zone. It's actually inside the hill radius where formally the gas is bound to the planet, but in practice the gas penetrates in from the protoplanetary disk on horseshoe orbits and then moves out again. And this is crucial because as the temperature is increasing down from the hill sphere down to the surface of the planet, there may be a water ice line sitting in this recycling zone. So what is the water ice line? Let me actually just go back a couple of slides. I was actually marking it here. The water ice line is pretty important. The water ice line is the distance from the star by which water will be in gaseous form on the inside and in ice form on the outside. I marked it here as 0.7 AU, and you can see we form dry planets inside the water ice line, wet planets outside, and then planets migrate, so you get a lot of wet planets inside of the water ice line also. Yeah. So if the water ice line is sitting at 0.7 AU, which you probably think it is, and Earth is forming outside of 0.7 AU, then we have to explain why Earth is not made out of 30% water, right? Because when we look at Earth's mass fraction of various volatiles, then Earth's oceans alone is only a few hundred ppm. That's not very much. Now we think inside of Earth's core, there's probably much more, so that Earth in total gets a few thousand ppm of water. Why is that? That's actually because when the water gets into the magma ocean, it also has to distribute between molten rock and molten iron, and water and also carbon and nitrogen are actually what we call siderophile elements. They tend to partition more into the iron. So a lot of the water that's accreted in the magma ocean is actually brought with these falling lumps of metal into the core. So there's a lot of volatiles in the core. So, but now we can make a model where Earth is growing outside the water ice line. It starts out dry, and then it's accreting. As it's accreting more and more, it's accreting these 30% ice pebbles, and it gets up to actually something like 10% ice at some point, which is much higher than where we want to end up. But then once you get to around 0.01 Earth masses, then it gets hot enough out here that the water is sublimated in this recycling zone. The water comes off and the water leaves, and then there's only dry pebbles being accreted from that point on. And that means that now we're accreting dry material all the way up to something like an Earth mass here, and then we're ending at a few thousand ppm, which is in pretty good agreement with the Earth's volatile content of water. So that was water. Two other important elements that are forming atmospheres is carbon and nitrogen. And where does carbon and nitrogen come from? Well, it probably comes from organic molecules, and I say this is not life, this is just organic molecules formed in the ISM, carbon rings, typically insoluble or organic material. The only role it plays here is not for life, it's only as a carbon and nitrogen carrier that's not ultra volatile. It's not N2, it's not CO. When it goes into organic molecules, they can actually survive up to 300 to 400 Kelvin. Very importantly, that also means that they will also undergo destruction while they're being accreted. The carbon turns into methane, the nitrogen typically into ammonia, which is all escaping easily. And then we can make exactly the same game as before. We can accrete these pebble rims with organic molecules. We can destroy them in this temperature range. And then we can start here at a few thousand ppm of carbon. That's what we probably have in the inner solar system. Got it? A few thousand ppm of carbon in the inner solar system, which we have from meteorite. And then we are accreting along. And at some point it gets so hot in the envelope that we are accreting less and less carbon. And we go down to maybe a few hundred ppm. And how much carbon should we aim for? That's actually a good question. Earth has almost no carbon in its atmosphere. Venus's atmosphere carries maybe a few 10 ppm of carbon if you divide by the whole planet mass, right? And again, carbon is strongly siderophile, so probably a lot of it is sitting inside the core. So we think we need probably a few hundred ppm of carbon. Very fine, we're landing in this range here. That's approximately good. It's actually even better with nitrogen. Earth's atmosphere is made out of a lot of nitrogen. Nitrogen is also siderophile. It also wants to go into the core, but nitrogen doesn't dissolve well in the magma ocean at all to begin with. So we think most of the nitrogen will be either in the mantle or in the outgas atmosphere. Look at Earth. Earth's nitrogen gives us 1 ppm. Venus's nitrogen, there's a lot of nitrogen in Venus's atmosphere, that gives us approximately 3 ppm. Maybe the missing 2 ppm of Earth is hiding in organic molecules that have been buried inside of the mantle. So now that we don't have the core reservoir problem, we can start with the 10 ppm nitrogen present in meteorites. We can undergo the destruction mechanism here, and we can go down to a few ppm, and therefore we can get a pretty good match to Earth's nitrogen content also. So pebble snow overall gives a good match to the observed, to the inferred H2O, C, and N content of Earth. Okay, just coming to my last slide, because this has some implications both for atmospheres and actually also for the origin of life. So, as I said, we have now dissolved our volatiles in the magma ocean. Now we need to get out of the magma ocean. We do that by crystallizing the magma ocean, typically from the bottom up when the planet stops to accrete. And then the magma ocean will outgas oxygen, H2, H2O, CO, CO2, and N2 as the major species. Importantly, I haven't talked too much about oxygen yet. It turns out the amount of oxygen that's outgassed here is not really determined so much by the accreted oxygen, it's more determined by this reaction here. Iron and oxygen makes oxidized iron. FeO is a mineral that sits not with the core, but with the mantle here. And the amount of oxygen in this reaction goes into equilibrium. The amount of oxygen outgassed is very, very little. And that actually will determine this speciation. When there's not much oxygen, this will go to H2. And CO, and the carbon will go to CO. And that's probably what happens with small planets like Mars. We believe that Mars would have outgassed an atmosphere that was strongly reducing H2 and CO. This is great news, by the way, for the origin of life, because maybe you know about the Urey-Miller experiment. You run lightning through a reducing atmosphere, you get all kinds of organic molecules, including HCN, which is very reactive. It can make amino acids and all kinds of things. So this is actually the best scenario we have for the origin of life. Problem is that this H2 is also lost very rapidly by XUV radiation. So it doesn't really survive very well. Reducing atmospheres are hard to hold on to. On the other hand, we also know from recent experiments in geochemistry and geophysics that when you go to a more and more massive planet, it tends to be more and more reducing, more and more oxidizing magma ocean. I have another reaction here, FeO plus a quarter O2 because FeO 1.5. This is Fe2 plus, two ionized Fe, this is Fe3 plus. At very high pressures in the magma ocean, the oxygen here, pressure here gets very high. This goes into this reaction here that makes a lot of Fe3 plus, so FeO 1.5. This outgasses a ton of O2 in equilibrium. And this means that an Earth mass planet, a massive planet that becomes oxidized by this process, will outgas H2O or CO2. Which is very different from our reducing atmosphere. That's totally different from our Urey-Miller experiment now, because these conditions, we are not really forming, let's get it down here. When you run lightning through an oxidizing atmosphere, you don't get HCN, you get something more like NO and so on, molecules that are not prebiotic in their nature. So when people are confronted with this, they say, well, then maybe there's another way that life could originate in oxidizing atmospheres. Just a tiny plot here where I show that deep down in the mantle, Fe2 plus, which is this molecule here, can react with water and make magnetite and make H2. H2 can then bubble up. And then some of the earliest metabolisms we have on Earth actually works on the on the chemistry of H2 and CO2. So you see, we're still reducing. We're not as reducing as here, but we have H2, we have CO2, and when these two things react, you can make methane, which gives you a lot of energy, and you can also make more complicated prebiotic chemistry. So overall, you can see here how I'm almost done here. Now, sort of a timeline, I would say, from the, if I can get my pointer back. I need to be, someone said I should be patient. I can point on the screen instead.
Okay, up or right, up or left?
I'll do that. No, got it. Never mind. So basically the idea is that we have a protoplanetary disk, it's filled with dust, it turns into pebbles, the pebbles are making planets, the pebbles are then raining down with the volatiles into the magma ocean. Now the magma ocean will expel these volatiles later to form an atmosphere, and this even has implications from the origin of life. So in my view, there's a whole connection between the ISM, the protoplanetary disk, planet formation, the atmosphere, and the origin of life, and I think that's a very exciting timeline that goes all the way through, with implications for the origin of life. And with that, I will simply thank you for your attention and take any questions.